Okay, today we're going to be checking out some of the best statistic videos on YouTube. And today we're going to be doing Crash Course. Now, I like Crash Course. I checked out Crash Course Philosophy a little while ago, and we may even get to that. But today we're doing statistics, because statistics is a way that people, the methods of statistics are used in pretty much every scientific discipline, and it's good to know a little bit about it. And honestly, I barely paid attention in college about statistics, and I regret it a whole lot. So today, we are getting better at statistics, and we're going to see what Crash Course has to say about it. And yeah, hopefully it will be as good as I think it will be. Let's find out.
Hi everybody, I'm Adrienne Hill. Welcome to Crash Course Statistics. And by everybody, I don't mean that literally. There are give or take 7.6 billion people in the world. When we hit 1 million views, that's still only 0.01% of the population. So maybe hi almost nobody? Statistics are everywhere. Some are explicitly part of our lives, like batting averages in baseball, expected goals in soccer, or the percent chance the meteorologist gives that it'll snow. They're in the stone-faced warning from your doctor, this procedure has a 2% chance of failure. Statistics make a very good case for not buying lottery tickets. Other times statistics are less obvious, but still with us. Insurers use them to set their rates. Researchers use them to try to figure out if a drug can actually help regrow the hair on the top of your head, or if there's a correlation between dog ownership and stress reduction. Big retailers hire statisticians to figure out how to market to us better. Apparently, Target can pinpoint when a pregnant woman might be due to give birth based on a change in what she buys. Stores also use statistics to figure out how to stock their shelves. Turns out a whole lot of people rush to buy strawberry Pop-Tarts before a hurricane hits. So in advance of storms, Walmart stocks up. For real. And statistics is central to some of the cool technology we use every day, like Siri and Alexa. Mark Twain popularized the quote, "There are 3 kinds of lies. Lies, damned lies, and statistics." And yes, statistics can be used to lie, but they can also be used to help find the truth. The purpose of statistics is to help find the truth. Statistics allow us to uncover simplicity inside complexity, to make sense of our world. And part of what we'll do in this series is figure out how to tell the difference between statistics used for good, understanding, truth-telling, and the statistics that we should question, that are being used to mischaracterize the world. Understanding.
And this is exactly why we're here, people. Because I want to be able to discern the difference between, or I want to be able to discern when statistics is used to lie and when it's used to tell the truth. And really, I think that can only come from having a understanding of the thing itself. And so that's what we're going to develop. We're going to watch this video, and we're going to get better at statistics than literally everyone in the whole world. You and me. You, the dear listener, and me. We're on this journey together. Thank you for joining me. It would probably help if I actually spoke into the microphone as opposed to the camera, but that's irrelevant. We're going to keep going.
How statistics work, even if you aren't running regressions for fun on the weekends, can help you ask good questions about other people's studies and discoveries. I'm Adrienne Hill. More than likely, I'll be your host for this series. There is a 1 in 74.8 million chance I will be killed this year by an asteroid or other near-Earth object collision. When I'm not hanging out here or researching the odds of death by freak accident, I work in public radio. I also co-hosted Crash Course Economics, where a statistically significant number of you who commented didn't like how and how much I move my hands. So I'm gonna work on it. I'm so excited for this series. Some of these are things I've thought about, some I'm gonna be learning along with you, and it's gonna be fun, because at the end of the day, statistics are about us, people, and our world, and how we relate to each other. I'll see you next week.
Not next week. Next second.
Hi, I'm Adrienne Hill, and this is Crash Course Statistics. Welcome to a world of probabilities, paradoxes, and p-values. There will be games and thought experiments and coin flipping. A lot of coin flipping. Statisticians love to talk about coin flipping. By the time we finish the course, you'll know why we use statistics and how, and what questions you ought to be asking when you run across statistics in the world, which is all the time. Statistics can help you make a guess whether or not you're going to be accepted to Harvard. Marketers use them to sell us gold lame pants. Netflix uses stats to predict what show we might want to watch next. You use statistics when you look at the weather forecast and decide what to wear, dress or jeans. Policymakers use them to decide whether or not to invest in more early childhood education, whether or not to spend more on mental health services.
I understand that nobody's here right now, but just to get in the habit of this streaming thing, I just want to take a moment to appreciate any viewers who are watching this right now or may watch it in the future. If you're enjoying the content, I would highly, highly recommend that you hit the like button, hit the subscribe button if you want. Make me the most popular person in the world. Get those numbers up, and then I recommend you provide me with finances to continue to do this, because this is clearly the best content in the world, and if you want more of this content, I need to make money, and I would love it if you would just give me your money, please. But only if you really, really want to. Actually, even if you don't want to. This is, in fact, a stick-up, and I need your money. So give it to me. I will put a link to my Patreon in the description. I haven't done that yet, but we're gonna get that there. And yeah, I just want to say I sincerely appreciate you joining me. I know I can put on a lot of irony. That's just par for the course. I am being kind of serious about wanting your money, but that's just, don't hate the player, hate the game. And this is the game we're playing, so, we know this. So we're going to keep watching here. I want to sincerely thank you for joining me, and we're going to keep digging right in.
Statistics is all about making sense of data and figuring out how to put that information to use. Today, we're going to answer the question, what is statistics?
So I have a filter on, and apparently the filter really
The
doesn't
legend
like
says that during a late
that
1920s
music.
English tea at Cambridge, a woman claimed that a cup of tea with milk added last tasted different than the tea where the milk was added first. The brilliant minds of the day immediately began to think of ways to test her claim. They organized 8 cups of tea in all sorts of patterns to see if she really could tell the difference between the milk first and the tea first cups. But even after they had seen her guesses, how could they really decide? Because she'd get about half the cups right just by randomly guessing either milk first or tea first, and even if she really could tell the difference, it's completely possible that she would miss a cup or two. So how could you tell if this woman was actually a tea savant? What's the line between lucky tea guesser and tea
Savant?
super taster? As fate would have it, future super statistician and part-time potato scientist Ronald A. Fisher was in attendance. During his lifetime, Fisher began work that set the stage for a large portion of statistics, which is the focus of this series. These statistics can help us make decisions in uncertain situations, tea taste tests and beyond.
There's something Fisher going on around here.
Fisher's insights into experimental design helped turn statistics into its own scientific discipline. And although Fisher didn't publish results of the tea test, the story has it the woman sorted all the teacups correctly, just in case you were curious. At this point, it's worth mentioning that there are 2 related but separate meanings of the word statistics. We can refer to the field of statistics, which is the study and practice of collecting and analyzing data, and we can talk about statistics as in facts about or summaries of data. To answer the question, what is statistics, we should first ask the question, what can statistics do? Let's say you wake up at your desk after a long
So we are determining what statistics is through a functional way of thinking about it, as opposed to a structural way. Though I don't know if you could really consider statistics in a structural way. I'm not sure what that would exactly entail. But Yeah, that seems to be the way that we're going to be starting off here with this lady. So let's keep going.
Evening studying for finals with a cheeseburger wrapper stuck to your face. And you wonder, why do I eat this stuff? Is fast food controlling my life? But then you tell yourself, no, it's just super convenient. But you're worried. You're thinking about how great it is that McDonald's serves breakfast all day right now. But maybe that's normal, right? I mean, finals are this week, so you Google the question fast food consumption, and you find the results of a fast food survey. The first thing you might do is start asking questions that interest you. For example, you could ask, why do people eat fast food? Do people eat more fast food on the weekend than on weekdays? Does eating fast food stress me out? Now that we have some interesting questions, we need to ask ourselves an even more important one. Can questions like these be answered by statistics? Like I mentioned earlier, statistics are tools for us to use, but they can't do all the heavy lifting. To answer the question about why people eat fast food, you can ask them to fill out a questionnaire, but you can't know whether their answers truly represent what they're thinking. Maybe they answer dishonestly because they don't want to admit that they scarf McDonald's because they're too tired to cook dinner, or because they're ashamed to admit they think Del Taco is delicious, or because none of the given answers represented their reasons, or they may not really know why they eat fast food. Armed with the results of the survey, you could tell that the most common reason that people reported eating fast food was convenience, or that the average number of meals they eat out in a week is 5. But you're not truly measuring why people eat so much fast food. You're measuring what we call a proxy, something that is related to what we want to measure, but isn't exactly what we want.
Okay, first definition of the day, we have proxy. I mean, there were technically other definitions going on here, but this seems to me to be the first thing that, well, it's the first thing I'm going to write down. We'll leave it at that. So a proxy is something related to what we want to measure. I mean, this makes sense, but isn't exactly what we want to measure. I mean, this makes sense. This is how I would use the word proxy. So we have this word proxy. It means sometimes as close as we can get is to something that might seem like it would indicate the idea we're looking for, but doesn't indicate it itself. I feel like there are probably some implications here about whether the proxy is in fact good enough to be associated with the thing we're trying to study itself. That's what I would imagine, but we'll find out if we go over that and how to come up with good proxies. That would make sense. So in statistics, it's important to be able to methodically come up with good proxies when we can't actually measure the thing itself. That tracks. All right, let's keep going.
Want to measure. To answer whether people eat more fast food on the weekends or whether eating it more than twice a week increases stress, we'd not only need to know how much people are eating fast food, which our questionnaire asked, but also which days they eat it. And we'd need an additional measure of stress. You can use statistics to give a good answer about whether you're going through the drive-thru more on the weekend, but even the question of whether eating fast food is associated with higher levels of stress is hard to answer directly. What is stress, and how can we measure it? And are people eating fast food because they're stressed? Or does eating all those calories make them stressed? It's often the case that some of the most interesting questions are the ones that can't be answered by statistics, like why people eat fast food. Instead, we find questions that we can answer, like whether people who eat fast food often work more than 80 hours a week. The tools we use to answer these questions are statistics plural, and there are two main types, descriptive and inferential. Descriptive statistics describe what the data show. Descriptive statistics usually include things like where the middle of the data is, what statisticians call measures of central tendency, and measures of how spread out the data are. They take huge amounts of information that may not make much intuitive sense to us.
Okay. Descriptive statistics. I feel like I want to hold on. Hold your horses. Okay. I am going to pull up my notes from last time. Open. Okay. Alright, so here are my notes from last time. Did I write anything down about descriptive versus inferential statistics? No, that does not appear that it was covered. We covered nominal or different types of data, categorical and numerical. We didn't cover different types of statistics. So we've got descriptive statistics. We've got the definition. Can I write the definition down? Hello? Come on. Oh my goodness. Come on. Okay. Includes things like where the middle of the data is. Bop, bop. What statisticians call measures of central tendency. Bop, bop. And measures of how spread out the data are.
They take huge amounts of information that may not make much intuitive sense to us and compress and summarize them to hopefully give us more useful information. Let's go to the thought bubble. You've been working for 2 years in the local waffle factory. Day in and day out, you create the golden browniest, tastiest frozen waffles ever created.
Sounds
the
like
holes
me.
are perfectly spaced, screaming for syrup. And now you want a raise. You deserve a raise. No one can make a waffle as well as you can. But how much do you ask for? An extra $1,000? An extra
Yes.
$5,000?
Yes.
You know you're valuable, but have no idea what other waffle makers get paid. So you dig around online and find there's an entire subreddit devoted to waffle makers. And someone, username Waffle Leaks, has posted a spreadsheet of waffle makers' salaries. Now, with a quick glance at this huge list of numbers, you can see whether the woman who works at a similar job at the rival frozen waffle company makes more than you. You can see how much more you're making than the new guy, who's just now learning to mix batter. But you still don't know much about the paychecks of your waffle company as a whole, or the industry, because it turns out there are thousands of waffle makers out there, and all you see is a list with data points, not patterns that can help you learn more about how much you might be able to convince the boss to pay you. Here is where descriptive statistics come in. You can calculate the average salary at your company, as well as how spread out everyone's salaries are around that average. You'd be able to see whether the CEO's paychecks are relatively close to the entry-level batter makers or incredibly far away, and how your salary compares to both of their salaries. You could calculate the average salary of everyone in the industry with your job title and see the high and low end of that pay. And then, armed with those descriptive statistics, you could confidently walk into the Waffle Boss's office and demand to be paid for your talents. Thanks, Thought Bubble. While descriptive statistics can be great, they only tell us the basics. Inferential statistics allows us to make inferences. Clever names, those statisticians. Inferential statistics allow us to make conclusions that extend beyond the data.
Okay. Bam, bam. Inferential statistics allow us to make conclusions that extend beyond data we have in hand. Period. Hand.
have in hand. Imagine you have a candy barrel full of saltwater taffy, some pink, some white, some yellow. If you wanted to know how many of each color you have, you could count them, one by one by one. That'd give you a set of descriptive statistics. But who has time for all that candy counting? Or you could grab a giant handful of taffy and count just those you've pulled out, which would be using descriptive statistics. If your candy was, in fact, mixed pretty evenly throughout the barrel and you got a big enough handful, you could use inferential statistics on that sample to estimate the content of the entire taffy stash. We ask inferential statistics to do all sorts of much more complicated work for us. Inferential statistics lets us test an idea or hypothesis, like answering whether people in the US under the age of 30 eat more fast food than people over 30. We don't survey every person to answer that question. Let's say someone tells you that their new brain vitamin, SmartyVite, improves your IQ. Do you rush out and buy it? What if they told you that the average IQ increase for Group A, 20 people who took SmartyVite for a month, was 2 IQ points, and the average IQ increase for Group B, 20 people who took nothing, was 1 IQ point? How about now? Still not sure? It's a pretty small difference, right? Inferential statistics give you the ability to test how likely it is that the two populations we sampled actually have different IQ increases. However, it's up to you as an individual to decide whether that's convincing or not. And don't be alarmed if the bar you set isn't the same in every situation.
It's not up to you as an individual, it's up to me as an individual. Okay?
Entirely okay to have different standards for the questions, does my cat like Fancy Feast more than Meow Mix, versus does this drug cure lung cancer? It might take more evidence to convince you to take a new, supposedly cancer-curing drug than to switch cat food brands. It should take more evidence to convince you to take a new, supposedly cancer-curing drug than to switch cat food brands. With inferential tests, there will always be some degree of uncertainty, since it can only tell you how likely something is or is not. Your job is to take that information and use it to make a decision despite that uncertainty. If statistics were a superhero, its bat call would be uncertainty, and its tagline would be, when you don't know for sure, but doing nothing isn't an option. Statistics are tools. Statistics help us make sense of the vast amount of information in the world. Just like our eyes and ears filter out unnecessary stimuli just to give us the best, most useful stuff, statistics help us filter the loads of data that come at us every day. Descriptive statistics make the data we get more digestible, even though we lose information about individual data points. Inferential statistics can help us make decisions about data when there's uncertainty, like whether SmartyVite will actually increase your IQ. But statistics can't do all the work. They're here to help us reason, not to reason for us. They can help us see through uncertainty, but they don't get rid of that uncertainty. To push our tool analogy a step further, statistics like chainsaws are pretty useless, even dangerous, without understanding how they work. We need to know how to use them and how not to use them. As we'll see in later episodes, statistics done poorly can lead us to some pretty silly conclusions, and chainsawing done poorly leads to about 36,000 injuries in the US each year, 81% of which are lacerations. Did you know that almost no one dies because of chainsaw injuries? Once in a while, but it's very rare. 95% of the people who are hurt by chainsaws are male. This does not necessarily tell us that males are significantly worse chainsawers. Statistics can help us plan a vacation to Bali in December. They can help us optimize our chances of winning our fantasy football league. They can help us budget our meal card at college. Statistics can help us decide whether...
Conquer the world? I didn't hear conquer the world on there anywhere. And I mean, that's why I'm here. So, I mean, lady, get with the program, huh?
That additional insurance the guy at Best Buy is trying to sell us on our new blender is actually worth it. Statistics can also help us decide whether or not to go ahead with an invasive heart surgery. Statistics can help NGOs optimize the amount of food aid they send to refugee camps. They can help policymakers decide if they should spend more or less money on helping students pay back their school loans, and can help you decide how much money you should be comfortable borrowing for college in the first place. There's a lot statistics can help us with, but some things statistics can't do. Thinking statistically means knowing the difference. So when your brother says he used statistics to prove that your mom loves him more, you can rest easy, knowing the only question he answered is whether she gives him slightly more ice cream each night. And you've got data suggesting she gives you extra sprinkles. Thanks for watching. I'll see you next time. Crash Course Statistics is filmed in the Chad and Stacy Immingholt studio.
Some kids don't get ice cream. Some kids don't deserve ice cream.
In Indianapolis, Indiana. And it's made.
Okay, so that was our first jaunt into statistics for the day. Once again, if you are enjoying this content, even though I don't think anyone here is here at the moment, thank you for being with me. If you have any money, I would appreciate it if you transfer that money to me, because I deserve it more than you, frankly. So, I'm just kidding. Okay, it's just a little irony. Relax. But also, if you are enjoying this content, please do consider making a donation. I am just getting in the habit of this thing. Once again, I don't even have my Patreon linked in the description. So if you have the keenness of mind to find out where and how to give me money, then I suggest you do so. I implore you to do so, and I hope that you do so. But if you don't, no hard feelings. You're just a terrible person. But also, I love you, and thank you for joining me today. We are going through the Crash Course Statistics series. We are in the process of exploring the best statistic courses that exist in the whole YouTube sphere. And we're trying to learn a little bit more about statistics. We want to get better, smarter, faster, stronger at understanding the world around us. Today and over the course of the series, we will be using statistics to do so. So thank you for joining me. And we are going to keep going here, running through this program. I don't even know how many of these episodes there are, but we're going to get as far as we can today. And I appreciate you being with me, really, truly, and sincerely. Anyone who finds this, thank you for watching. Okay, and on to the next episode. We're going to just click our little button here and find out what comes next. And it's Mathematical Thinking Crash Course Statistics number 2.
Hi, I'm Adrienne Hill. This
Hey,
is
Adrienne
Crash Course
Hill.
Statistics. In the last video, we talked about why we care about statistics, how we use statistics. And statistics is math. So we thought we'd take a detour today from the traditional curriculum to talk about how to think about numbers. Really, really big numbers, really, really small numbers, and how to make sense of them. We're also going to talk about mathematical thinking and fighter jets. Chances are, if you're watching this channel, and certainly if you're commenting below, you're literate. You understand language and how to use it. But are you equally comfortable with numbers? And I'm
No.
not talking here about being able to calculate square roots in your head, or instantly tell whether or not 17,321 is prime or not. And it is. I looked it up. Numeracy is about being able to wrap your head around what it means when politicians talk about a $1.5 trillion budget hole. It's about getting a handle on how much you should really lose sleep over the chance of an Ebola outbreak, and how to compare that risk to the chance of being killed by a terrorist.
I mean, to be fair, I feel like numeracy is also about being able to do square roots in your head, but, you know, who's judging?
Or a snake bite, or dying from an opioid overdose. And it's about what those comparisons might tell us about the time and resources we spend trying to address those problems. Mathematical thinking is about seeing the world in a different way, which means sometimes seeing beyond our intuition or gut feeling. Because it turns out most of our guts are good at digesting food and pretty bad at math. Infants, less.
Is mathematical thinking about seeing the world in a different way? Pretty sure mathematical thinking is about thinking about math, thinking of seeing the world in a mathematical way. I mean, different from what? Different from, I guess, the average way that people think, but isn't that mathematically how we think about that? I mean, I suppose that's not, what do you call it? When most people talk about averages, they're not really, like, colloquially, when we say average, like, we're not, I mean, we are talking about math, but people aren't thinking really about math. Or are they? I don't know. Anyway, I don't think that mathematical thinking is about seeing the world in a different way. That's a weird, bizarrely uninformative way of talking about it. But I understand this is a simple course meant to be, broken down easily. And so I probably, if I had to steel man the case for that description, what they mean is like, math is a particular way of viewing the world, and we don't tend to think about math, we don't tend to think about things in a mathematical way. Therefore, insofar as math is different from how we typically think about it, it is different from, it's a different sort of way of thinking about things. But still, fairly unclear and unformative little segment there. He said very judgmentally,
Less than a year old can discern between three objects. I am much more advanced than an infant and can pretty easily comprehend the difference in 1 and 100, even the difference between 100 and 1,000, or maybe even 10,000. For most of us, once numbers get really big, we lose our ability to have any intuitive sense of them. The distinction between a million and a billion and a trillion is really hard to visualize. There are 100 trillion bacteria in each of our bodies in non-mathematical guts. 100
Nice.
trillion. There are an estimated 10 quintillion insects that are alive right now, and an
And
estimated 300
lowering every
sextillion
second.
stars in the universe.
Nice.
So how do you even begin to think about those big numbers and what they mean? Let's go to the thought bubble. Take a minute to visualize the difference between 1 and 100, and 1,000, and 100,000, and a million. That's a lot of dots. A whole lot of dots. There are other good ways to try to make sense of big numbers. You can try to put the number in context. The U.S. debt is in the neighborhood of $20 trillion. About 323 million people live in the U.S. So the debt owed for each person is about $62,500. You can also turn a big number into...
Okay, so the title of this video is Mathematical Thinking, and I'm just gonna state the obvious here and say, okay, what they're trying to do is show us how math is related to statistics, right? And it seems that the thesis of this video is to help us get an intuitive sense for big numbers. So that seems to be the central thesis here, is how do we get an intuitive sense for what these big numbers that statistics often play with in terms of data. What we learned last time was, what was it? Hold on. We call it numerical data, which can be either discrete or continuous. We're trying to get a sense for what that data feels like intuitively or through basically visualization. That seems to be the thesis of this video so far. Haven't finished it yet. We will figure that out as we go along.
to a unit of measurement that you're more comfortable with. The Kola Super Deep borehole, which is the deepest artificial point on Earth, is 40,230 feet deep. I have no idea how deep that is until you tell me that it's about 7.5 miles down, and I can start to picture it. You can also have reference points for big numbers ready to go. There are about 100,000 words in a 400-page novel. About 46,000 people show up to Dodgers games in Los Angeles. I can roughly visualize that. 1 million people taking to the streets to protest might be easier to think of as 21 Dodger stadiums worth of people, or 14.5 crowds for a Real Madrid match. Time can help us go even bigger. 1 million seconds is a little less than 12 days. But what about 1 billion seconds? Do you think you are 1 billion seconds old? Well, are you older than 32? It takes 32 years for 1 billion seconds to pass. And what about 1 trillion seconds? Think you or I will be alive after 1 trillion seconds passes? Sorry to break it to you, but we will not. Even if you are destined to be the Guinness Book of World Records oldest woman, there is a 100% chance, barring massive medical breakthroughs, that you will be dead. It takes 32,000 years for 1 trillion seconds to tick by. Thanks, Thought Bubble. A quick note about scientific notation. Scientific notation can be really helpful for calculating with big numbers, but not necessarily helpful for understanding them. Without context, exponents can be non-intuitive, if that's a word, in their own way.
What did I
10 to
say?
the
What did I
39th
say?
and 10 to the 32nd sound like they might be close, but 10 to the 39th is 10 million times larger than 10 to the 32nd. We're not going to run the dots on that one. There are about 7.6 billion people on Earth. 7.6 billion. Understanding the sheer number of people out there in the world can help us make sense of the commonness of coincidences or improbable events. Some statisticians call it the law of truly large numbers. The idea here is that with a large enough group or sample, unlikely things are completely likely to happen. Consider this example from statistician David Hand. On September 6, 2009, the Bulgarian lottery randomly selected as the winning numbers 4, 15, 23, 24, 35, and 42. And then, 4 days later, on September 10th, the Bulgarian lottery randomly selected new winning numbers. 4, 15, 23, 24, 35, and 42. Exactly the same numbers. People freaked out. Bulgaria's sports minister ordered an investigation. Was it fraud? Something else? Hand says, calm down. It's just coincidence. He lays out the math to prove it, but part of the argument here is the law of truly large numbers. If you consider the number of lotto drawings every week around the world over years and years, it would be amazing, he wrote, if draws did not occasionally repeat. Speaking of those incredibly unlikely things, we need to talk about the flip side of incredibly big numbers, the incredibly small numbers that can also be hard to comprehend. Take the likelihood of winning a Mega Millions jackpot in the US. Right now it's about 1 in 302.6 million. The probability that you'd win a jackpot is 0.00000003305. Let's put the teeny tiny chance of that happening in some perspective. 302.6 million is the number of seconds in more than 9.5 years. So to borrow here from a very funny post by Tim Urban on Wait But Why, that's like knowing that a hedgehog will sneeze once in the next 9.5 years and betting on the exact second during those 9.5 years that the hedgehog will need a tissue. And I'm going with May 2nd, 2:23 and 33 seconds p.m. 2021. Our inability to judge small numbers does more than just cause us to misjudge our chances of winning the lottery. It causes us to worry about the wrong things, to fear the wrong things. Take your chance of dying from Ebola. If you live in the US, the chance that you'll be killed by Ebola in any given year is pretty close to your chance of winning the Mega Millions lottery. 1 in 309.6 million. It is among the very, very least likely ways anybody living in the US will die in a year. Though you are, by some accounts, less likely to be killed by a terrorist attack in the US committed by a refugee. In a 2016 study, researchers calculated that as a 1 in 3.64 billion chance in the US in a given year. And you're far more likely to die in dozens of other ways. There's a 1 in 6 million chance someone living in the US will be killed in a given year by a bee sting. A 1 in 708,000 chance they'll die falling from a ladder. A 1 in 538 chance they'll die.
I'm starting to feel like I should never leave my house. I don't know. There's just something, just a strange coincidence that I'm getting that sense. Maybe I should just, never leave my house. I mean, I don't know why. Just a sudden feeling.
In a given year from cancer. And not a big cause of death. But did you know that people die in sand holes that they or their friends have dug out at the beach? They crawl in, looking for a little time in a sand hole, and whoosh, the hole suddenly collapses, and they're buried. Stay out of sand holes. I'm gonna stop because it's stressing me out. The point here is that it's worth taking the time to think through small numbers, because they can help you figure out what's actually worth worrying about and what isn't, what you might want to act on, and what you might want society to take more and less seriously. My personal takeaway is that I'd be way better off spending more time exercising and less time looking around obsessively for poisonous snakes, because the annual odds of dying from a snake bite in the US are only about 1 in 34 million, but the odds of dying from heart disease in any given year are 1 in 534. Thinking mathematically isn't just about understanding numbers better. It's about asking important questions about the world around us and letting numbers illuminate those questions. One of my favorite examples of mathematical thinking is the story of Abraham Wald and the missing bullet holes. Hat tip here to mathematician Jordan Ellenberg for highlighting the story. Let's go to the news desk. World War II, Manhattan. A group of statisticians and mathematicians are hard at work trying to protect American fighter pilots. Their task, trying to figure out how best to armor planes without making them too heavy, so our heroes can outrun and outwit the enemy. In an effort to figure out how best to protect our planes, the statisticians pore over data of the planes that returned from fighting, looking at where they took damage, where the bullet holes were. That data showed there were more bullet holes in the fuselage and fuel system, and not as many in the engines. So how do we save our American heroes? The exceptional statistician Abraham Wald studied the data and came back with advice that surprised everyone: to put the armor where the bullet holes weren't, over the engines. Wald realized the bullet holes should have been more evenly distributed over the planes. If fewer planes were returning with holes in the engines, that meant those planes weren't returning home. Wald had the exceptional realization the data wasn't a random sample of all planes. It only represented the planes that returned. He suggested the military add armor to the engines. American lives were saved. Not all mathematical thinking is going to help you save lives, but it will help you make better decisions. Mathematical thinking can help you see past coincidence. It can help you judge risks. It can help you see the broader relationships in the world. Thinking mathematically gives us something to go on other than our guts and their trillions of bacteria. Thanks for watching. I'll see you again next time. Crash Course Statistics is filmed in the Chad and Stacy Emigholz studio in Indianapolis.
All right, that was certainly a video. All in all, a lot of words to say. Basically, let's develop some more intuitive sense, mathematical sense for what large and small numbers are. Probably could have been said in a much shorter time period, but this is the edutainment industry. It wouldn't be fun without some anecdotal and little pieces of factoids and stuff. So, tolerable, if a little time wasting, but we're not here to listen efficiently. We're here to learn statistics and rate statistical videos for this series. So, I didn't rate the last one. I'm going to rate this one. I'll give it like a B minus C. I'll give it a C plus. I didn't really learn too much. The thesis was kind of but I understand we're just getting started out here. Maybe we'll get into some more juicy details in the future videos. And also, I just want to take a moment to thank you for joining me. I know no one is here right now, but if you were here, you would be enjoying this. And if you were enjoying it, you would have no choice but to provide me with some amount of your financial means to support this kind of entertainment. And I would greatly appreciate that from you. In this hypothetical situation, my appreciation would extend to the ends of the earth, and you would feel that appreciation and slowly develop that parasocial relationship with me that would compel you to continually give me more and more of your money. And once again, I would appreciate it. Thank you for joining me today. We're going to keep plowing through here through Crash Course Philosophy Statistics on to the next video. And I just want to say thank you for joining me, and let's get on to the next video.
Hi, I'm Adrienne Hill, and welcome to
Hello,
Crash Course
Adrienne Hill.
Statistics. In the last video, we tried to make sense of ginormous numbers and teeny tiny numbers.
That's not a
Today,
real
we're
word.
going to talk about less showing numbers. The numbers stuck in the middle, the averages, the medians, the modes. They may not seem as mind-blowing or all that flashy, but turns out they're really, really important. Those middle numbers are often the ones that get all the press attention, get tossed back and forth in political debate, and they give us this little fun bit of trivia. What's the average or mean number of feet people have? It's not 2. Turns out the average number of feet people have is a little less than 2, because the average takes into account the small number of people out there with fewer than 2 feet. So if you have 2 feet, you have more than the average number of feet. And with that, let's get into measures of central tendency and why they're useful. If your boss asks you for a report on this quarter's sales numbers, but is rushing to a meeting and only has time to listen to one piece of information about that data,
Okay, so today we're going to be talking about, where this video is about, she said central Tendency. Did I spell that right? I don't care. All right,
That
let's go.
piece of information you give her should probably be a measure of central tendency. The center of a bunch of data points is usually a good example or summary of the type of data we can expect from the group as a whole. One common measure of the middle is the mean. You've likely heard it called the average, though all of these measures are sometimes called averages. Some people call the mean the expectation of a set of data. The mean, or average, takes the sum of all the numbers in a data set and divides by the number of data points. So if 10 pregnant dogs give birth to 50 total puppies, the average litter size is 5 puppies. Each data point, in this case each litter of puppies, contributes equally to the calculation. Aww. Here's another example. Say you have $10 and your best friend has $20. The mean amount of cash you two have is $15. 10 plus 20 divided by 2. But saying that the mean is $15 doesn't mean you each can buy that $12 BFF necklace that you've been eyeing. You know, the one with half a heart that fits together? You personally only have $10 in your pocket. The average of a set of data points tells us something about the data as a whole, but it doesn't tell us about individual data points. The mean is good at measuring things that are relatively normally distributed. Normal means a distribution of data that has roughly the same amount of data on either side of the middle and has its most common values right around the
Definition time. Oh, let me, this is... normal. A distribution of data that is roughly the same amount of data on either side of the middle, and has its most common values around the middle. I'm assuming this is the bell curve, as we learned, not the book. Okay, relax. Values around the middle of the data. Like the last video we watched, or not the last video, but from the last stream, if you were cool enough to have been around for that, then yeah, we learned, I believe we learned about this, and this is just basically a normal distribution, is that little belly shape. Yeah, the bell shape. Okay, we will find out.
middle of the data. Data that are distributed normally have a symmetrical bell
See?
shape that you've
I was
probably
right.
seen before. A distribution shows us how often each value occurs in our dataset, which is known as their frequency. Imagine you're trying to impress your new college dorm mates by guessing how many times they've each seen Harry Potter and the Sorcerer's Stone. Your mom is in the entertainment industry, and you overheard at her last dinner party that 18-year-olds on average had seen the movie 5 times each. That's a lot of Quidditch. So you should guess your new friends have seen the movie 5 times each, unless you can clearly see Slytherin tattoos. You won't be right each time, but it's your best guess. It might not be the best way to impress them, though. It's really not a great party trick. Sometimes the mean is misleading. For instance, life expectancy in the Middle Ages. As we explored in Crash Course World History, there was an incredibly high rate of infant mortality in the days before modern medicine. But the people who made it to adulthood lived relatively long lives. Because of the high rate of infant and child mortality, the average life expectancy was about 30 years. But things weren't nearly as dire as all that. Not if you actually made it to 30. In the 13th century, a male who lived to 30 was likely to make it to his 50s. To give unusually large or small values, also called outliers, less influence on our measure of where the center of our data is, we can use the median. Unlike the mean, the median doesn't use the value of every data point in its calculation. The median is the middle number if we lined up our data from smallest to largest. For example, if you have 2 cats, Jillian has 1 cat, and Eric has 3 cats, the median number of cats in your little cat-loving group would be 2. When we put the number of cats in order from the least to the most cats, 2 is in the middle. But what if there's no middle number? You invite Will to join your cat group. He has an impressive, or is it excessive, total of 14 cats. Now there are 4 cat owners.
Not excessive.
There is no one middle number. Both 2 and 3 are in the middle. In this case, there are differing opinions on how to calculate the median, but most often we take the mean of the 2 middle numbers. So our median would be 2.5 cats. Meow, meow, me. Let's go to the thought bubble. Imagine 10 artists have been working for years together to come up with a new, fresh way to tie macrame knots. The standard square knot just wasn't inspiring them the way it used to. And finally, they do. Voila, the abracadabra Doolittle knot. So these 10 artists go out to celebrate, and they go to a relatively modestly priced restaurant because macrame artists just don't make all that much money. Each of them pulls in about $20,000 a year. So the average or mean income around the table is $20,000, and the median income is also $20,000. Now let's imagine that Elon Musk gets wind of this macrame milestone. Turns out he's a huge macrame fan himself. Beauty in design. He couldn't miss up a chance to celebrate, so he decides to show up at the restaurant. Musk's total annual compensation, including his salary and stock options, is reportedly in the neighborhood of $100 million. As soon as Musk walks in the door, the average income in the room skyrockets to a little over $9 million. But nobody else in the room is actually richer. Nobody feels any richer. The median income of the macrame artist and Musk is still $20,000 because most of our group is still making $20,000. And this isn't just the stuff of our make-believe macrame world. It happens in real life too. The average is distorted by outliers. Thanks, Thought Bubble. All right, now say there's a controversial book on Amazon called Pineapple Belongs on Pizza with 400 reviews, 200 5-star reviews, and 200 1-star reviews.
Okay, so this is an obvious point, but also I think an important one to underline. Oh, stop it. Chill, bro. Chill. Sure. Okay, so the mean can be distorted by outliers. Thus, to rely on the mean, depending on the purpose of the data, would be a mistake. Sometimes.
The mean number of stars given was 3, but no one in our sample actually gave the book 3 stars, just like no one could actually have the median of 2.5 cats. In both of these situations, it can be useful to look at the mode. The word mode comes from the Latin word modus, which means manner, fashion, or style, and gives us the French expression a la mode, meaning fashionable. Just like the most popular and fashionable trends, the mode is the most popular value. But we don't mean popular like Despacito popular. When we refer to the mode of our data, we mean the value that appears most in our data set. For our Amazon reviews of Pineapple Belongs on Pizza, the modes are both 5 and 1, which gives us a better understanding of how people feel about the book. These reviews are called bimodal because there are 2 values that are most common. Bimodal data is an example of multimodal data, which has many values that are similarly common. Usually multimodal data results from 2 or more underlying groups all being measured together.
Okay. Seems pertinent. Okay. Oh my goodness. Bang bang. Bimodal data is an example of multimodal data and indicates probably 2 underlying groups all being measured together.
In the case of our book, the 2 groups were the Love It 5-star group and the 1-star group. Or for another example, if we made a graph of the times customers went in and out, we'd probably see 2 peaks because there's 2 groups of people, one around lunchtime and one around dinner time. The mode is useful here because it's an actual value that occurs in our data set, unlike the median and mean, which can give us numbers that wouldn't actually occur and don't describe our data very well. The mean time people come into in and out may very well be 3:30 p.m., but that doesn't suggest you should expect an overflowing restaurant in the middle of the afternoon. You should be able to get your animal-style burger and fries without too much of a wait. The mode is most useful when you have a relatively large sample so that you have a large number of the population.
The mode is most valuable. Sorry, useful. That's an interesting conflation. When you have relatively relatively large sample. So that you have a large number of the popular
values. One other benefit of the mode is that it can be used with data that isn't numeric. Like if I ask everyone their favorite color, I could have a mode of blue. There's no such thing as a mean or average favorite color. The relationship between the mean, median, and mode can tell us a lot about the distribution of the data. In a normal distribution that we mentioned earlier, they're all the same. We know that the middle value of the data, the median, is also the most common, the mode, and is the peak of the distribution. The fact that the median and mean are the same tells us the distribution is symmetric, that there's equal amount of data on either side of the median and equal amounts on either side of the mean. Statisticians say the normal distribution has 0 skew since the mean and median are the same. When the mean and median are different, a distribution is skewed, which is a way of saying that there are some unusually extreme values on one side of our distribution, either large or small in our data set. With a skewed distribution, the mode will be the highest point on the distribution, and the median will stay in the middle, but the mean will be pulled toward the unusual values. So if the mean is a lot higher than the median and mode, that tells you there's a value or values that are relatively large in your data set. And a mean that's a lot lower than your median and mode tells you there's a value or values that are relatively small in your data set. Let's go to the news desk. The average income of a U.S. family grew 4% between 2010 and 2013. Those average paychecks expanded from $84,000 to over $87,000. But not everyone is cheering. The median income fell 5% during those same years. Median family income dropped from $49,000 to just over $46,500. This really happened back in the years after the financial crisis. The mean income rose at the same time the median income fell. That's because families at the top of the income distribution were making more money and pushing the mean up, while many other families were making less. And even though unscrupulous politicians could accurately claim average incomes are rising and pat themselves on the back, it would be misleading. For most Americans during that stretch, incomes were flat or falling. This points to another really important point about statistics, a point we'll come back to time and time again in this series. Statistics can be simultaneously true and deceptive, and an important part of statistics is understanding which questions you're trying to answer, and whether or not the information you have is answering those questions. Statistics can help us make decisions, but we've all got to use our common sense and a little skepticism. Thanks for watching. I'll see you next time. Crash Course Statistics is filmed in the Chad and Stacy
All right, that is the end of this video. So how do we feel about it? I give this one a B. I mean, it was talking about a very simple concepts, the mean, median, and mode, but it kind of connected it to, well, it did connect it to some things we learned in the last stream where they talked about skewed data. And what I found informative about this video was the fact that she more directly drew out the connection between the mean, median, and mode as it relates to skewed data. So we got to see that the mean is going to be I think it was the furthest right. The median is going to be right in the middle, and the mode is going to be the top of the data peak in skew data. And I thought that was an interesting point that I don't know I would have had the acute intelligence to be able to determine in such a way. oh, sorry. Oh, okay. All right, I'm not gonna lie, guys. Statistics is cool and everything, but I think my coffee's wearing off, and I'm getting a little tired. I'm gonna keep crunching through, but I don't think I'm gonna be able to maintain the superior level of entertainment that I've been providing so far. I think it's gonna dip a little bit. So I want to just say that I appreciate you bearing with me, and I think now would be a good opportunity to keep doing my practice, which is to beg, what's the word? Shamelessly for your money. I understand you work very hard for your money, and that money is very deserved, and you dear listener, are a god. You are deserving of that money, and I just want to say, any amount you contribute, I value it so much, so much. Thank you for your contributions. Thank you for watching this incredibly high value entertainment, and I just want to say, I appreciate you bearing with me while we watch Crash Course Statistics, and we all get better at learning about how to make sense of the world through numbers. We're going to keep crushing it while we watch these videos, and I hope that you find this valuable, and I hope it brightens your day. I hope it improves your day to such a degree that you realize your value in life and achieve everything you might ever want. And with that, I am going to click the next button, and we're going to watch the next video.
Hi, I'm Adrienne Hill, and welcome to Crash Course Statistics. So in the last episode, we talked about the middle of sets of data, what statisticians call the central tendency. Today, we're headed to the data on both sides of that middle, what statisticians call measures of spread. Not to be confused with the gauge of the quality of my peanut butter and jelly sandwich. Measures of spread, right? Get it? Because you spread the peanut butter and jelly?
That was horrible.
Anyway, statistical measures of spread, or dispersion, tell us how data is spread around the middle. That lets us know how well the mean or median represents the data, and how much we trust conclusions based on the mean and median. And I can hear you saying to the screen, come on, Adrienne, when would anyone use this in real life? I may or may not have said that too at some point. I have no official comment. But measures of spread are all around, from test scores, like when you find out you scored in the 99th percentile on the LSAT. Economists use measures of spread to study income inequality. Investors use them to try to identify price bubbles they might want to try to avoid. Gamblers use them to try to figure out how much they might win or lose. Pollsters use measures of spread to help calculate margins of error. So yeah, they come up in real life. And heads up, there's some math coming your way. We're not going to spend a lot of this series doing calculations, but for this one, it's important.
Give me the math. Math me.
Let's do a thought experiment to compare measures of spread. And since you're probably watching this on YouTube right now, we'll talk about YouTube viewers and their ages. You're a YouTuber with big dreams and amazing content, but as a growing channel, you need to know more about your audience. YouTube will give you some information.
How does she know? How did she know? She was speaking to me directly. How did she know? Wow. I feel so seen. Wow. I'm like, am I that famous? Am I pre-famous? Wow. Wow. Okay, let's keep going.
information about this, usually in the form of a fancy chart. One of the pieces of information you could calculate is the range of your audience's age. Range takes the largest number in our data set and subtracts the smallest number in the set to give us the distance between these two extremes. The larger the distance, the more spread out our data is. With the range, we're able to quantify the distance between our most extreme points. We can often sense that groups are different, and our ranges confirm it. If we looked at the range of your audience's age, we'd get a better idea of the full spectrum of the people who watch. If you have 13-year-olds watching, you might want to limit the adult content. But if you have people over 40 watching, you may still need to explain some of the slang you're using. Hashtag lit, hashtag fam. Am I doing that correctly? But the range won't tell you about your core audience. These are the people who you appeal to most. This might be better summarized by the interquartile range, or IQR, which does...
Ooh, a definition. Time to bring out our handy dandy notepad. IQR. Jargon. Now let's talk about a little bit about jargon, right? So at base of my philosophy, I believe. Let me explain something to you, okay? I'm working on fleshing out my philosophy, and aside from the fact that, okay, I gotta work on concising my language. Okay. I believe at base, biology is true. It's likely to be true. It's probably true. And what I mean by that is, broadly speaking, the epistemic project of biology uses methods that lead to some kind of truth. Okay? So there can be philosophical dispute, there can be disputes about what kinds of methodologies are the best, but broadly speaking, we like biology. We think things like evolution are likely to be true. Given the evidence, we believe that evidence is a valid form of truth finding, and we believe that adaptation happens, right? So why I bring all of this up is I believe that every piece of, I believe that, how do I say this? Human minds are good at niching into particular niches. You like that redundancy? Yeah, so basically, humans are natural creatures. We exist in nature, and an aspect of nature is that organisms adapt to their environment, right? And are adapted to their environment, right? And I think our minds are an extension of that because they are emerged from the biology of it. So minds are meant to adapt an organism to its environment, right? So human minds in particular are particularly adaptive at creating, you could call them false environments, so that's not quite right. I would call them environments that aren't, let's say, artificial environments. So think about like games, broadly speaking, like sports, video games, whatever. These are situations we put ourselves in and we adapt to. So all of this to say that jargon is an important piece of that puzzle, because human minds use jargon to basically signal the kind of environment they're in. So right now we're looking at statistics, and statistics is, well, it's a topic. Topic, I believe, I could be wrong, and I probably am, but topic is related to topical, which is related to topography. I think that, that might even be wrong, but let's just say, for the sake of argument, that it's right. Let's say a false thing is true, right? This is loosely how I think about it. So you have a topic, or topography, right? A topic is sort of a lay of the land of an ideascape. Y'all like that? How's that for some jargon? Ideascape, right? So you have this ideascape that we inhabit. It's a sort of a way of looking at the world, right? So here we are, we're studying statistics, and we're trying to embed ourselves in this kind of ideascape of statistics, right? What it's a subject matter, right? We are in it. We are trying to become very privy statisticians here, right? So here we are learning a piece of jargon, and a jargon is basically an element within this ideascape. It's a way of tuning our attention to an aspect of the environment. So I'm just bringing this sort of meta analysis into not in the research paper sense, but in the just me speaking off the cuff sense, right? So we're talking about statistics, and here we have a piece of jargon, and I just really wanted to bring your attention to really appreciate the process that's going on here. Maybe you don't see the things that maybe you don't see things the way that I see them, okay? And that is perfectly fine. Your experience is valid, and your reality, your truth is a valid truth, okay? Even if you're wrong. Whoa, 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 whoa. Not sure why that happened. Anyway, your truth is valid, and I just want to let you know that. But also, so we have a piece of jargon here, and basically all of this was to say that jargon is a way of attuning our attention to a particular environmental ideascape, okay? You got all that? Do you write that down? Do you find that useful? Remember to smash that like button. Remember to hit that subscribe button. Remember to tell your family you love them, and unless they're awful, then avoid them at all costs for your mental health. And with all that being said, let's continue writing down some jargon while we attune our attention to become the best statisticians ever in all the land. Okay? Okay? Interquartile range. Now that's some really good jargon. Interquartile range. It doesn't consider extreme values. This content is very dry, y'all, so I appreciate you bearing with me, even though you're non-existent at the moment. I believe very much in if I build it, you will come. I think you're there. You're there as, you're like, what's it called? In physics, there's kinetic and potential energy. You're like my potential audience. It's like I build the content, you're not there yet, but I've lifted the rock high up into the air, and right now it is still, but the potential energy is high. It is high, and all that needs to be done is for that release. Okay? So, thank you, potential audience, for being there, supporting me for all these years. Okay? Extreme values. The IQR. Okay, so we gotta be fancy, right? Not only do we have the jargon, but we have the abbreviations for the jargon. That's how you know you're really part of the group. You don't say the jargon, you say the acronyms for the jargon. So interquartile range, the IQR, looks at the spread of the middle 50% of your data.
Doesn't consider extreme values. The IQR looks at the spread of the middle 50% of your data. So in this example, the ages of your audience. The IQR will give you a better idea who is the primary group watching you. A lifestyle guru like Bethany Mota might have an IQR of 13 to 25, whereas I might guess somebody like John Oliver has an IQR that's older, maybe in the range of 22 to 40. Their overall range could be similar. I'm sure there are 13-year-olds and 60-year-olds watching both of those channels, but the IQR gives us a better idea of their core audience. So let's introduce some numbers and do a little math. Let's say 10 basketball players have scored the following number of points in the first part of a game. 1, 3, 3, 4, 5, 6, 6, 7, 8, and 8. The median is 5.5. That divides the data into two halves. To divide it further into quarters, we find the median of each of those halves, which are 3 and 7, Q1 and Q3, respectively. The four quartiles here are from 1 to 3, 3 to 5.5, 5.5 to 7, and 7 to 8. The IQR is the difference between Q3 and Q1, or in this case, 7 minus 3, which is 4. If the median is closer to one of the ends of the interquartile range, it means that quartile has a smaller range. Since each quartile has the same number of data points, it means that for that quartile, the same amount of points are closer to each other. But we're still losing a lot of information about how spread out all of the data is, since only 2 of the data points are being used to calculate both the range and the interquartile range. There are measures of spread that include all of our data, just like the mean. Take the variance, which can give us a better sense of how spread out the whole data set is. Let's take a scatter plot of all our data points and draw it.
Okay, let's take a moment to appreciate what we learned last time. Okay, so I believe we covered variance, right? I believe. Distribution, blah, 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 blah. I guess not. Okay. Anyway.
A straight line across the graph at the mean. Then draw lines from each point straight down to the mean line. Those lines represent the deviation, or difference, from each point to the mean. Now imagine a square with sides the length of the deviation line. The area of all the squares for every point divided by the number of data points is the variance. But it turns out that if you use this same formula to calculate the variance of a sample, it would be biased. That is, the sample.
You know, I just realized I'm not keeping good enough track of these videos. So what did I give? I forget. I think I gave the last video B+. B+. Okay, so this one is CCS number 4. We learned about the interquartile range. This one is about measures of spread. That if you use the same formula to calculate the variance of a sample, it would be biased. That is, the sample variance would consistently be of a little smaller. So now we're starting to get at the edge of my comprehension ability. Maybe because my coffee is wearing off, and maybe because it's a pretty dry subject. But okay. Let's get into it. Okay, variance would be the real variance of the population. All right, well, let's just keep watching. We're gonna have to find some way to assess this video without me falling asleep. Okay, let's crush it.
Variance would consistently be a little smaller than the real variance of the population. We divide by the number of samples minus 1 in order to get the sample variance to be unbiased, or a better guess for the population variance. For example, say that the Mets, the Yankees, the Angels, the Dodgers, and the Astros have 2, 2, 5, 8, and 8 wins each. The mean number of wins for the group of teams is 5. 25 divided by 5. To calculate the variance, we take each number and subtract the mean, square this difference, then add all of these squared differences together and divide by the number of data points minus 1. The variance of this set of baseball teams is 9 plus 9 plus 0 plus 9 plus 9, all divided by 4, which equals 9 squared wins. And yes, I know 9 squared wins doesn't mean anything, but when we square our numbers, we're also squaring our units right along with them. Even though squared wins isn't an understandable unit to us, the variance is still a really useful number to have because it tells us how much variability is in our data. In our baseball example, it tells us roughly how far each team's win record is from the mean. We'll see it pop up quite often once we get to inferential statistics. For now, let's go to the thought bubble. Professor Hooch has hired you to analyze students' broom speeds for the Hogwarts Quidditch teams. There are 15 new Gryffindors, so you measure how long it takes them to fly around twice. And here's the plot of the times, in seconds, that it takes each student to complete the trip. Looks like a few of the Muggle-born students who didn't grow up using magic brooms took a lot longer than their classmates who grew up in wizarding families. Our mean of all students is 36.47 seconds. But if we take out the Muggle-born students, the mean is down to 29.67 seconds. Means are very easily changed by extreme values. But the median doesn't change as much. It only goes from 30 seconds to 29.5 seconds when we pull out the Muggle-borns. The range changes greatly, going from 46 seconds to 20 seconds, because the extreme values determine the high number in our range calculation. The variance is also greatly affected, since those slow Muggle-born students inflate our mean. If we take out those Muggle-born times, the rest of our data is quite close together, reflected in the variance of about 36 seconds squared. But once we add those times back in, the variance shoots up to about 228 seconds squared, which matches our intuition that the group is now more spread out. You can see that the distance between points and the new mean are much larger than before we put the Muggle-born times back in. These Muggle-born times change our measures of spread, but that doesn't necessarily mean these data are bad. We need to think about whether unusual points belong in our data or not. And we'll talk more about unusual points, or outliers, a little later in the series. Thanks, Thought Bubble. Remember that the units of variance are squared units, like seconds squared for our flying broomstick times, or baseball wins squared for our baseball example. And yes, variance is valuable, but sometimes we need something with units that make just a little more sense. Enter standard deviation. The standard deviation is the square root of the variance, which...
Ooh. The standard, how do you spell it? It's with a D. Deviation is the square root of the variance. Did I spell root right? No, I didn't. It's not root, it's root. Duh. Is the square root of the variance, which gives back the units. Gives back the units
that we're comfortable with, seconds, or baseball wins. The standard deviation of our Quidditch data would be about 6 seconds without the Muggle-born data, and about 15 seconds with it. You can think of the standard deviation as the average amount we expect a point to differ or deviate from the mean.
Okay. The average amount we expect a point to differ or deviate from the mean. Okay. Yeah. So now we've learned a little bit more jargon, the standard deviation. So we've got two words here. We've got standard and we've got deviation. Another way of thinking about the word standard is average, the average deviation, and from that we can say the average amount we expect a point to deviate or differ. So the average difference or the standard deviation, right? So they say standard deviation to indicate the average, but I'm just saying it a couple times so it gets into my head. I need it in my head. Anyway. Okay. Standard deviations. A point to differ or deviate from the mean. The mean.
That means that on average, we expect students to deviate from the mean time by 6 seconds. When the Muggle-born students raise our standard deviation goes up as well. In part, this happens because now the other points are further from the mean, since the mean became larger. Just like the mean, the standard deviation and variance are heavily affected by unusually large or small values. So you should still always look out for extreme values in your data and be aware of the influence they can have. If you see someone reporting on a mean number in an article or on television, you can use the standard deviation, if they're thoughtful enough to give it to you, to get a better understanding of how well the mean represents the data. If the mean number of murders per state in 2015 was 307,
Nice.
which it was, then a standard deviation of 10 murders shows us that 307 is a pretty good guess for the number of murders in any individual state. But if the standard deviation was 353 murders, which it was, that guess wouldn't be nearly as accurate. And this makes some sense. You wouldn't expect Montana to have nearly as many murders as a heavily populated state like New York or California. So let's go back to our YouTube channel. So now you have a better idea of who's watching you, and you're getting more and more viewers every day. If you want to grow more, you realize you need to diversify your audience. So you look at the standard deviation of the ages of your audience. This will give you a better idea of whether your audience have similar ages or whether you're appealing to many age groups. You keep adding new content and collaborating with other YouTubers to try to reach a wider audience, and it's working. Your standard deviation is getting larger, which means you're attracting a more diverse or more spread out audience. And congratulations! Looks like you just hit 1 million subscribers. As our YouTube thought experiment showed us, the different measures of spread each give us different information about our data, but they all tell us something about how spread out the data are. Sure, you can use measures of spread to grow your YouTube channel, and they're important for statisticians, but they're also valuable for us non-statisticians to ponder. And I'm going to go a little deep here and try not to veer into the cheesy, but here's my big takeaway from this episode. We all have a tendency to compare ourselves to the average. We compare our income to the average income. We compare our rent to the average rent, our intelligence to the average intelligence. We compare our weight to the average weight of someone our age, and on and on. From these measures of spread, I take away the idea that the average whatever on its own can be deeply misleading. Comparing ourselves to that single statistic can give us a false sense of failure or success, depending on how the data is spread out. So maybe stop comparing yourself to the average. Or if you're really insistent on ranking yourself against everybody else, go calculate the standard deviation too. Thanks for watching. I'll see you next time.
I don't need to look at the data. I know I'm the best. We're the best. We have the best entertainment. We are the best we're the best statistical live streamers that exist. We're the only ones that exist. And I just want to take this moment at the end of this video to tell my potential audience how much I will appreciate you when you finally show up. I will treat you well. I will treat you better than any other YouTuber. And I just want to say thank you for joining me on this adventure through life, through the difficulties, through the ups and the downs. I just want to say thank you so much for joining me as we go on this adventure. And if you are finding this content at least enjoyable, if the standard deviation is high enough, that's not how you use that word, but that's how I'm using it. If you feel like you want to deviate from the average, which is to not donate anything, and to actually give me some money, I would greatly appreciate it. I thank you for your time, for your attention, for everything you do in sitting there, tolerating me, watching me, telling me how amazing I am. I just want to say thank you. Thank you so much. Now, we're going to keep plowing through because our goal is to become the best statisticians that exist. It's a word. Check it out. Look it up. Okay? We're going to become the best at statistics. You and me. Just you and me. We're going to do it. We're on a team. We're going to be the best at understanding studies, understanding the world around us. And yeah, so we're plowing through. Last time, we watched a video by some guy. I forget his name, but you can go check it out on the live section of this channel. And now we're going through the Crash Course Statistics channel. Now, we just finished up this video. On this video, we talked about standard deviation, we talked about variance, we talked about, I think it was called interquartile range. And we learned some valuable things. Will I remember them? I don't know. But this isn't where we're stopping. This is not where the adventure stops. This is just beginning. And we are we're going to keep plowing through. Now, in terms of substance, I would rate this video probably an A minus. We learned a fair amount. We learned some good jargon terms, some nice juicy jargon terms. I was able to talk to you a little bit about my philosophy, about how the world is. And, we really grew as humans. So I'm just going to keep plugging through. We're going to see how much growth, how much personal growth we can achieve. Thank you for joining me. Ooh. Okay. Charts are like pasta. So here we're gonna just do a little enter. So I rated this rating, we'll say an A minus. A minus. Good job, lady. I'll get your name eventually. So this one we're gonna call Crash CCS number 5. Look at us go. Charts are like pasta. Data visualization part 1.
Hi, I'm Adrienne Hill, and this is
Adrienne Hill. That's her name. Adrienne Hill.
Crash Course Statistics. So for the last few episodes, we've discussed ways to summarize data using numbers. We used measures of central tendency and measures of spread. But sometimes it can be helpful to actually see your data in addition to having numbers to describe it. Data visualizations are important to understand because you'll see them pretty much every day in the news, on Facebook, and magazines. Maybe I'll make an infographic of all the places we see data visualizations. There are two main types of data that we might encounter, categorical and quantitative. Quantitative data are quantities, numbers that have both order and consistent spacing. For example, how many ounces of olive oil are in each American home? If 3 families told you how many ounces of olive oil they have, you could put them in a meaningful order, from least to greatest, or greatest.
Okay, here we are covering stuff that we covered on the last stream from the other guy. So we are introducing the concept in this course of categorical versus quantitative data.
This order also has consistent spacing. An increase in 1 ounce of olive oil is the same whether you go from 0 to 1 ounce or from 100 to 101 ounces. These properties allow us to do simple math with the data, like taking the mean or calculating the standard deviation. Categorical data doesn't have a meaningful order or consistent spacing. For example, favorite kind of pasta. You might like
So quantitative has order and spacing. Categorical doesn't.
Penne, rotini, linguine, even angel hair. But there's no objective way to put those pastas into a meaningful order. Is penne truly better than linguine? Where does rotini fit in? It would be pasta
Rotini is the best. This lady, clearly this lady is wrong. Okay? Saying we can't judge these things. We can definitely judge these things, okay? This lady doesn't know what she's talking about. Rotini, then penne, then linguine. Or linguine, then penne. I mean, they're both lesser pastas, okay? But clearly rotini is the best, okay? I don't know. I think this lady is basically discredited, but we're going to keep watching anyway.
goodness, to try to put them in order. The simplest way to display categorical data is to make a frequency table. A frequency table shows you all the categories and all the numbers of data points that fall in that category. In other words, it's frequency. To change a frequency table into a relative frequency table, we just need to take each raw frequency and divide by the number of total points to get a decimal.
Hold on.
The simplest way to display categorical data is to make a frequency table.
Frequency table. Okay. How to display categorical data? Use a frequency table. What is a frequency table?
Frequency table shows you all the categories and all the numbers of data points that fall in that category.
Shows all categories and all data points that fall in that category. Okay?
Frequency table shows you all the categories and all the numbers of data points that fall in that category. In other words, it's frequency. To change a frequency table into a relative frequency table, we just need to take each raw frequency and divide by the number of total points to get a decimal.
Relative frequency table involves taking frequency and dividing by total to get percentage. Cool.
Between 0 and 1. Some of you may be used to reading decimals as percentages, but if you're not, just multiply by 100 to get the percentage. For Linguini, we have 10 divided by 50, which is 0.2 or 20% of the group. Relative frequency tables have the benefit of being easy to compare. No matter what we're measuring or how many data points we have, it's easy to compare percentages. If 20% of people like Linguini, we can see that's a smaller percent than the 67% of people who like pineapple on pizza, or greater than the 10% of my family who think statistics are scary. The relative frequency table for favorite pasta might look like this. We can also add more than one variable to our frequency table. We could ask people to rate their favorite pasta sauce and make a combined frequency table, or a contingency table of both pasta and sauce preference. If I were planning a party and needed to pick some pasta for the group, my best bets would be the rotini with red sauce and penne with red or white sauce.
True.
And because I'm planning a party and because I'm having food, I did look it up. The chance of death by choking on food in the U.S. in a given year is 1 in 100,686. But sometimes we don't want just numbers in our visualization. Earlier in the series, I talked about how it can be hard to wrap your head around numbers, especially when they get really big or really small. There are other, more visual ways to represent categorical data. One way to do this is with a bar chart. A bar chart uses the frequencies that we saw in our frequency table to create bars that have a height equal to the frequency. That way, we can compare the height of bars instead of looking at raw numbers. Here's a bar chart representing the pasta data we saw in our original frequency table. You can see that penne is by far the most chosen pasta, and how it compares to angel hair. Bar charts display a lot of information in a very simple graph. They can also display the frequencies of multiple variables. Let's say we want to compare each of these pasta types with either red or white sauce. We can either stack frequencies, so it gives us the same information as our contingency table, or we can have bar charts side by side. Pie charts are another way of displaying categorical data. They use the relative frequency of categories to portion out pieces of a circle, just like a pie. The higher the relative frequency, the bigger the slice of pie a category gets. Pie charts are useful because our eyes are pretty good at comparing slices. Our pasta data in a pie chart looks like this. Pie charts are great at visually displaying one variable, but they struggle to effectively display.
Hold on. This pasta chart is clearly wrong, okay? Because rotini is smaller than penne, when rotini is clearly the superior pasta. Penne is basic pasta, and I will not tolerate this kind of misinformation being spread, alright? So someone needs to contact this lady and tell her how wrong this chart actually is, okay? And how wrong people are if this is true, okay? They need to change it up, change their minds, and come to the right side of history, Okay.
More than one variable, like our pasta and sauces contingency table. Another way to display categorical data is a pictograph. Pictographs represent frequency with pictures. A picture, like the ball in this basketball participation graph, will represent some number of units, say 100 kids. So if Riverdale High had 550 students participate in their basketball programs, then the graph would show 5.5 basketballs. Sometimes pictographs represent frequencies by increasing the size of the picture instead. And it's not wrong, but it's more difficult for us to visually compare, especially for small differences, which can be misleading. Plus, at a casual glance, we don't know what the size difference means. Are we comparing the diameter of the basketballs, or are we comparing their areas? This is Channel 2 News. Looks like all you students out there are really hitting the books. Data from the U.S. Department of Education shows the graduation rate has been climbing. So way to go, everybody. You're passing the test of life with flying colors. Let's push that stack of books even higher. So that last pictograph, not at all to scale. See how the stacks of the books are not proportionate? It shows a difference of 5%, from 75% to 80%, with a stack of books that is over double the height of the 75% stack. This makes the difference seem huge because the axis doesn't start at 0. And yet, an increase of 80 to 81% is shown by two stacks that are barely different in height, even though the 5% difference looks huge. Always keep an eye on those axes. Let's loop back to quantitative data, which, as you'll remember, have a meaningful order and consistent spacing. Frequency tables can also be used to display quantitative data, like age or height or ounces of olive oil in your house. We just have to create categories out of our quantitative data first. We do that with a process called binning. Binning takes a quantitative variable and bins it into categories that are either pre-existing or...
Nice. More jargon. Gonna catch all the jargon. Binning takes a quantitative variable and bins it into categories that are either pre-existing, like my audience, which, well, my audience is a potential audience, or made up.
Made up. For example, I can say that 0 to 15 ounces of olive oil is very little, 16 to 32 ounces is average, 33 to 49 ounces is a lot, and 50 plus ounces is excessive. Like suspiciously excessive. Like Will's 14 cats excessive. Why do you need so much olive oil? Anyway, once I've binned my data, I can create a frequency table, or relative frequency table, just like with our pasta example. It might look something like this. Binning is most useful when there's pre-existing bins for our data. Like you can divide age and years into the bins, child, teen, adult, and older adult, because those are pre-existing categories. We can also take a score on a depression test and create two bins, clinically depressed and not clinically depressed. You can see from this example that bins don't have to be equally spaced, but if you see quantitative data that has been binned, make sure that the way it's divided up was appropriate for the situation. Unequally spaced bins can be misleading unless there's a real-world distinction to back it up. Say politician X wants to make himself look popular, but it seems like people in their 30s really hate him, probably because he said the reason they can't afford a house is their brunch habit. Politician X wants to hide the fact that over 80% of people in their 30s say they won't vote for him. So he does some rebinning. Traditionally,
I hate to say this, but, hot take, avocado toast is mid, okay? It's not great. I mean, it's not bad. It's just kind of, there's something else I feel similarly. Oh, yeah, pineapple pizza. Pineapple pizza it's fine, it's fine. And I get it, avocado is very fatty. It's supposed to be like butter, It's fine, If someone was like, here, eat this avocado toast, I wouldn't be like, ew, gross, no. But I'd probably be like, okay, I wouldn't be like, hell yeah, I'll eat that avocado toast. I mean, maybe with a little salt on top, maybe with I don't know, something else with it, but just avocado on toast, it's fine, it's not anything to write home about. I don't know why it was ever so popular, other than like avocados are pretty tasty. Um, honestly, think like guacamole toast would be better. Honestly, like than just avocado, like guacamole toast. Then we're like moving into better territory, but not just avocado toast. Anyway,
Data are banned roughly by decade. 18 years old to 29 years old, 30 years old to 39 years old, 40 to 49. You get the point. But Mr. X needs to hide those hateful 30-somethings in the data. The old chart looked like this, but politician X decided to split up the 30-somethings to make his numbers look better. He moved the data around to hide the glaring group of 30-year-old dissenters. Instead of showing the truth that 30-somethings despise him, we see a more positive view of his popularity. By splitting the 30-somethings and putting some of them into two other larger groups, he can obscure their political dissatisfaction.
okay, I think this is an important spot to underline. So here, we're seeing a way that we can lie with data, and this is good to notice because I don't know that I would have noticed this. Look, just come with me on this adventure. Look, we have 18 to 29. 30 to 39, 40 to 49, 50 to 59. So that's, decades going on here, right? Here we have 18 to 32, 33 to 55. Like that's not, I don't think that's even the same distance, right? It's not. 56 to 59, like why would you make that such a short distance, So yeah, I think it's important that we just underscore this moment and just like breathe it in. This is what lying looks like. And if we just take a moment and really appreciate, like, over here we have the bins, right? All evenly distributed. And over here we have the bins all, like, mishmashed and weirdly, some are long, some are short. Then it all makes all the percentages look all pretty. Like, just breathe in the lie. Just breathe it in. Appreciate it. Take this moment of lying out with you into the world. Recognize it in the wild and apply it to your own life. This is how you too could lie with data. That is the other side. That is the dark side of what we're learning here. Okay? And I'm not here to tell you what to do, just to judge you if you do it that way. Okay? So yes, breathe it in. Okay. Take a moment. All right.
Looking at this new table, he'd win the popularity vote in each of the 5 new bins. If I don't show you the number of voters per bin, it seems legit. Another categorical graphing method we can apply to quantitative data is bar charts. When we use bar charts for quantitative data, we squish the
I love when it gets out of sync. That's like my favorite thing.
bars together so that they're touching, and we call them histograms. The bars are squished together because the data are continuous, which means the values in one bar flow into the next bar. There's no separation like in our categorical bar charts. In histograms, like bar charts, the height of the bars tell us how frequently data in a certain range occur. A histogram also gives us information about how the data is distributed. We can estimate where the mean, median, and mode of our data are, as well as how spread out the data is. Look at this histogram for our olive oil data. For this histogram, we can see that the range of data is approximately 85, since it covers the value from 0 to 85 ounces, and that it's right skewed, the tail is to the right, and that its center is around 25 ounces. The histogram gives us more information about the data than a frequency table does, but they're still obscuring what the specific data values are. If you read the news or watch the news, you will see these representations over and over and over. You will likely see far more of these charts and graphs than you will create. The big takeaway here, as a consumer of these things, is to look closely at what the visualization is actually telling you, or maybe trying to hide from you. These charts and graphs give us another way to comprehend numbers and to see the big picture. Thanks for watching. I'll see you next week. Crash Course Statistics is filmed in the Chad and Stacy Immigholt studio in Indianapolis, Indiana, and it's made with the help.
All right. Wow, guys. Thank you for being here. Thank you. so much. Now give me just one moment. I just need to do some little bit of housekeeping. Just double checking on some things. Oh look, there I am. There I am. For the world to see. Ooh. MIT has an introduction to statistics course. I'm not showing you guys this because, frankly, you don't deserve to see this. Okay, the course is from 5 years ago. Well, it's from 2016. I feel like, yeah, 2016 is more than 5 years ago. We're just gonna save that. Save. Gonna add that to statistics courses. And we are gonna create and then I want to check to see how many more episodes are in this. Wow, there are 44 episodes in this. 44. We're definitely not getting through all of this today. I need to take like a moment, take a breather, take a chill pill. We're gonna just see how our friends over with the Nalanda debate folk are doing. If you've been with this channel, you will notice, and I don't think there's many of you, but assuming you are one of my loyal followers from the start, you will notice that I've done previous streams about Nalanda debate, which is like Buddhist arguing. And they recently put out a video about 10 days ago with a whole 42 views. And we're going to see how you can free your mind from negative emotions with the logic of Nalanda debate. And it's just 6 minutes and 50 seconds. It's going to be a little brain cleanser before we get into some more stats stuff. So we're going to just take a look here. Just got it pulled up. Oopsies. Alright. Hold on. There. Now you can see.
Hi, and welcome back to Nalanda, India's ancient wisdom. I'm Tenzin Namjong,
Ancient.
and this is lesson 2B. In the last lesson, we started to discuss the purpose and value of debate. We'll continue on that theme in this lesson, but here we're going to focus on what for most of us will be the more wide-reaching and practical purpose of debate. That is, to be able to develop our capacity to regulate our emotions in daily life, to stop the cognitive biases that stimulate destructive emotions, and to respond to the world with a balanced mind and kind heart. Although you may never have formally learned the structure of debate, nor how to form a logical syllogism, everyone repeatedly engages in reasoning to justify their ideas, feelings, and actions.
Should they?
Let me give you an example. Say you're walking out of the store with your hands full of bags, and the person in front of you, instead of holding the door open for you, lets it slam behind him and into your face. How rude, your mind's
Okay, that was pretty funny. That was pretty funny how they made the Buddhist monk be the rude guy. I'll give him that. That was funny.
screams. And even though you're not harmed and manage to make it out of the store and onto the street without any real hardship, you can't help but brood. The incident is over, never to be relived again, but in your mind it keeps playing over and over. What's more, the image of that person who let that door shut keeps thrusting.
This is why you can't trust Buddhists, everyone. You can't trust them. You just can't. Because of stuff like this. You know? They're admitting to it. They don't hold doors open. Where's chivalry? Where's goodness, huh? In old times, the Buddhists were actually super duper nice. But here we see like times have changed. This young generation of Buddhists, they're just not the same. They lacked the Buddha Chitta of days of old, you know. It's just disappointing.
Itself into the forefront of your mind. He's selfish. He's a jerk. Everyone around here is a jerk.
True.
This city is just awful. No one here gives you the time of day. I deserve better than this.
You
I
do.
try so hard to be considerate, and this is
You
what I get.
do.
My day is ruined.
Okay, maybe that's a little exaggerated, but really, not by that much. This is how our mind works, because we never call into question the reasons that play out in our minds and fuel our feelings. Even if there's not a conscious process of reasoning, there's always some underlying logical structure supporting our emotional reactions. I'm upset because this city is horrible. This city is horrible because everyone here is a jerk. And everyone here is a jerk because this one person here is a jerk. And this person is a jerk because he didn't hold open the door for me when I was leaving the store.
Man, I don't see any issues with that logic at all. It was pretty solid. It was like, you know, hard to debate with that.
Now, is any one of those reasons actually a valid and correct reason?
Yes.
If we learn about what it takes for something to be a flawless reason, we'll see that most of the time the
Flawless.
reasons we hold on to an event that incite our worst moods, that fuel our anxieties and insecurities, are simply wrong. They don't hold up to reality, but to see what holds up to reality and what doesn't, we need to learn, and we need most especially to think, reflect and analyse. As we do so, we begin to get a clearer picture of how our minds function, of the interactive nature of mind and the world it experiences. We realise how anger and getting annoyed are just silly, and what's more, are controllable.
If you have feelings, y'all, you're just silly. Okay. You are being ridiculous, and you should just get over it. I love how gaslighty this video is. It's just like, just change your mind. Have you tried changing your mind? Have you tried thinking about things differently?
Eventually, we gain the mental flexibility and discipline to regulate our emotions.
Why is this guy riding a unicycle? Like, what's... Oh, I guess he's juggling his different personalities. I guess that different feelings or whatever. But it's like, it's a metaphor for like how precarious that can be. Deep.
By examining the makeup of our inner and outer worlds and analysing how those things exist, we develop an ability to maintain a joyful, peaceful and wise frame of mind. This frame of mind
And if you can't, you're a bad person.
becomes your best friend wherever you go, because it keeps you free of problems. Unlike the typical mind state we have that constantly whispers deceiving thoughts and assumes that I and my feelings are an exception to the rules of logic. By becoming more aware of our own emotions and how they invariably are stimulated and accompanied by how we're thinking, we'll naturally become skeptical about this self-centered outlook and an intrinsic cognitive bias that lies at the heart of most of the problems we create for ourselves. The bias which favours an in-group at the expense of an out-group. We can then be kinder to both ourselves and others, more accepting, forgiving, and loving towards whomever we come across, and thus directly benefit the wider world.
Now, this is all about debate as it's been traditionally used in the context in which it was developed. That is, in Tibetan Buddhist monasteries, where the students are actively working on inner, spiritual practice to overcome their self-centered tendencies. But, as mentioned in the previous lesson, the uses of debate certainly don't need to end there. Through learning debate, you develop analytical skills that allow you to develop a more refined view of reality. And this skill is applicable in all fields, not just Buddhist philosophy. Think about these questions.
Is light a particle or a wave, or both? Does cutting taxes on the rich or raising taxes on the rich benefit the economy more? How do we draw the lines between species or define a planet? What is a human right, and what is the responsibility of governments and the public to protect and provide for those rights?
Sorry, you may have noticed that the light behind me just cut out. That's one of the challenges of shooting in a non-professional video. Yeah? I don't want to criticize. Yeah. That's one of the challenges of shooting in a non-professional environment. Okay.
Okay. Those people seem to be doing well enough. I actually did have fun. In case you didn't watch my other stuff, and I imagine most of you have not, I went through this Nalanda debate school thing, and it's a pretty fun little format. You know, it's like a game. You know, there's a little format. You assert something, and you try to get the other person to like contradict themselves by like either agreeing or disagreeing with what you're saying. That's basically the short and the long of it. But it was pretty fun. Had fun debating with people. Does it develop these analytical skills? I mean, I don't think there's enough research on it yet to really make assertions about it, but it's certainly a fun little activity. Oof. Alright, so I am going to cancel out of that. And we are going to continue our statistics journey. Alright, did I rate this video yet? What am I going to rate this video? Data visualization, they went over bar charts. I'm not sure what I'm going to rate it. I'm getting kind of bored. I'm going to rate it a B. Because I feel like it. We're just going to call it a B and call it a day. Call it a B and call it a day for that one. And we're going to move to the next one. Okay, so there's like 40 some odd videos in this series and we're on number 5. So am I going to get to 10 today? Probably not, considering I've been doing this for 2 hours now and we've only gone through 5 videos, which is like, it's almost an hour worth of content, right? Because each video is approximately 10 minutes long. I mean, I think the intro video was only like 2 minutes long, so we're moving on to the next one that we're going to keep plowing through. And, you know, to my potential audience, because it's been a few minutes since I've said it, just the long and the short is, if you enjoy this content, give me your money. And if you don't enjoy this content, give me your money. It's that simple. And I haven't if you don't feel like I've earned that right from you to ask for that, then that's okay. Your feelings are valid, but if you do feel like I deserve a little bit of your money because of the value I've created in your life, then do consider making a donation. I will put links in the description at some point, and you can focus your financial concentration on that. And with that being said, I'm going to move on to the next video. Thank you for joining me. Thank you for sharing your time with me. And with that, we're going to go to visualization part 2. And we're going to pop that puppy up on the big screen and dig in.
Hi, I'm Adrienne Hill. Welcome back to Crash Course Statistics. Last time we left off talking about different data visualizations, the ones we encounter every single day. Whether it's a chart on the subway telling us the prevalence of heart disease in different age groups, or a histogram on BuzzFeed showing us how many times people use Lyft each week. These visualizations allow us to get to know data with our eyes. And today we'll dive deeper into data visualization and make all sorts of beautiful graphs and talk about some really extreme situations, like the person who watched Sandy Wexler on Netflix like 400 times, which seems high. Last episode, we looked at histograms, which use the height of a bar to show how frequently data occur. We can also use this format to make a dot plot. A dot plot takes a histogram and replaces...
Okay. CS number 6. Plots, outliers, and Justin Timberlake. Data visualization part 2. Rating. We'll need that. Now we're going to talk about dot plots. Takes a histogram and replaces the solid bars.
This is the solid bars, which use their height to show frequency with dots. There's one dot for each data point contained in the bar, so we can just count the number of dots to find out how many there are. The dot plot for our olive oil data looks like this, unsurprisingly similar to the histogram for that data. Or check out this dot plot of how often this sample of people called their moms this month. This gives us a nice way to explore the general shape of our data. But we still lose information about the individual data values, just like with the histogram. Occasionally, we want that extra information. Enter the stem and leaf plot. A stem and leaf plot is a cousin of the dot plot. It also gives us information about data and their frequencies by stacking objects on top of each other. However, stem and leaf plots use values from the raw data instead of dots. So we'll turn our olive oil dot plot into a stem and leaf plot. And no, I'm not going to explain my olive oil fixation. First, we need to split each data value into a stem and leaf. Stems are related to the bends, or bars, in our histogram or dot plot. Take our dot plot, for example. Each stack of dots might represent a range of 5 ounces, from 0 to 4 ounces, 5 to 9 ounces, all the way up to a bar with all the data in the 80 to 84 ounce range. The stem for a bin of data is the digits that all the values in the bin have in common. For the 10 to 14 ounce range, each value has a 1 at the beginning of the number, so the stem is 1. For the 80 to 84 ounce range, the data all have an 8 at the beginning, so the stem would be 8. We can have larger stems too. If the data went all the way up to 2006 ounces, we could have a stem of 200, but that's probably too much for our olive oil example. Now that we have all of our stems, we can add the leaves. Each stem, like in a real plant, can have multiple leaves. They're stacked on top of each other so that the height of the stack shows you how frequently data appear in that bin. just like a dot plot. The actual leaf is the rest of the digits that are not in the stem. If one of our data points is 13, and the stem for that range is 1, that takes care of the 1. So the leaf is 3. Leaves appear in numerical order from the stem out. So leaves that are smaller digits are closer to the stem. From a distance, stem and leaf plots look a lot like a dot plot or histogram. If you squint your eyes, the leaves almost look like bars or dots. Unsquinting them will allow you to see even more information than a histogram or dot plot will tell you. You get to see what the individual values are and how they're spread out within a bar. Stem and leaf plots are usually flipped on their sides, so the stems are listed vertically and the leaves extend horizontally. Here's a stem and leaf plot of the number of pieces of gum each of your extended family members has chewed in the last month. Now let's talk about box plots. Box plots use some of our measures of central tendency and spread to visually display.
Okay, so we've learned about dot plots, learned about stem and leaf plots, which are dot plots on their side with the first number of a range at the bottom, the side. Now we're talking about box plots.
Our data. A box plot is also called a box and whiskers plot. It has two major parts, the box and
I remember this. Box and whisker plot.
the whiskers. The box is a rectangle that stretches across the interquartile range of our data, from Q1 to Q3. At the median, there's a line splitting the rectangle into halves. If one
box covers Q1 to Q3, line with a median, the middle of a box.
one of those halves is larger than the other, that quartile is more spread out. Since each quartile has the same number of data points, the smaller the quartile, the less spread out that portion of the data is. Imagine the difference between fitting 20 clowns in a
That's
car
horrifying.
and fitting 20 clowns in a regulation-sized football field. Same number of clowns, more space to make balloon animals. Attached to either end of this box are the whiskers, which help show the minimum and maximum of all the data, as long as it's within 1.5 times the interquartile range of the median. This value sets our fences. We use 1.5 times the interquartile range because most of the data will be within this range, especially if your data is normally distributed. We'll get into this more in future episodes. Most of the data will be inside the fences. Any data outside is flagged as a potential outlier. It can be tempting to think of outliers as data that's wrong somehow, but that's not always the case. Values outside the whiskers are less likely than data near the box plot, but they're not impossible. For example, it's pretty unlikely that if you dial random numbers into your phone, you'll call a Domino's pizza, but it is possible. Rare values do happen. Keeping those rare but possible values can be important. When the local news shows you a box plot of local rents and decides that the bottom 1,000 rent values are outliers, the graph they display could be misleading. Those rents are real values that you could expect. Taking them out will make your visualization less informative and might lead you to think that the average rent is higher than it actually is. However, some values that are flagged as outliers may not be expected in your data at all. Perhaps Neymar snuck into your amateur pickup soccer game without you knowing. His off-the-charts agility scores are not representative of the population you're interested in, since he's Neymar, not an amateur. Or maybe you made a typo on your spreadsheet and wrote 500 pounds instead of 5 pounds for your data on the weights of pet teacup pigs. That'd be a giant teacup pig. The problem is, you may not always know the difference between a point that's valid but rare and one that's a mistake. Since we need a way to decide, it's useful to have a preset cutoff for when we discard the data. To see how box plots can help us look for these outliers and compare data from 2 samples, let's jump to the thought bubble. Justin Timberlake has a new album. This American-born singer and songwriter has had quite the career. I mean, he did bring sexy back. Our writer Chelsea wanted to know how going solo affected the songs he wrote. Specifically, she wanted to know the number of unique words he used per song. To satisfy her curiosity, she made a box plot for a sample of Justin Timberlake songs once he'd gone solo, and one for a sample of songs he sang with NSYNC. The first thing we might notice is that the medians are pretty different. The median number of unique words in a Justin Timberlake song is higher than the median number of unique words in an NSYNC song. JT has a median of 129 words versus a median of 89 back in his NSYNC days. Guess we shouldn't be surprised coming from a band that had a song titled Bye Bye Bye. So it seems like JT may have developed a larger lyrical vocabulary when he went solo. Maybe Lance Bass was holding him back. Anyway, you might also notice that the box part of the NSYNC box plot is a lot smaller. The squish nature of the box plot shows us that NSYNC songs have a relatively similar amount of unique words. The box plot also shows you some potential outliers to look at, shown by the points that are outside the fences of our box plot. Let's look at a song that's marked as a potential outlier in the Justin Timberlake box plot. The song is Chop Me Up, and it has 257 unique words, which is a lot since the median number of unique words for a JT song is 129. It's definitely outside the fences. Thanks, Thought Bubble. We don't want to throw out data just because it's extreme, and Chop Me Up isn't part of some super experimental Christmas album, so it's hard to tell if this is a valid data point. To get around this uncertainty, we apply our preset rule. There isn't one set rule for handling these extreme values. There are many. For now, we'll use our box plot method and get rid of the Chop Me Up data because it's outside the fences. Remember, statistics is all about uncertainty. I'm not sure if the number of unique words in Chop Me Up is just a rare value or whether it's the lyrical equivalent of Neymar in a pickup soccer game. We still have to make decisions. For all the nerd fighters out there, you may have heard of Hank's annual Nerdfighteria census, and while you're interested in taking it, you might wonder how long it takes to fill out. You don't have all day. So you use your new data viz skills to create a box plot of the data, and wah wah. I can't even see the box or the whiskers through all those extreme values. It looks like some nerd fighters were very thorough or were very distracted by other things. 8,000 minutes is 133 hours. The plot isn't wrong per se, but it's not very informative since we can't get much useful information from it. We don't have any better idea of how long it's going to take to fill out Hank's survey. When you make or see a data visualization, it's important to remember that its job is to actually give you information. If it doesn't do that, it's not worthwhile. Now let's go back to frequency plots and talk about one last method for visualizing quantitative data, the cumulative frequency plot. Cumulative frequency plots are like histograms, but instead of the height of a bar telling you how much data is in that specific bin, it tells you how much data is in that bin and all previous bins. That's why it's called cumulative. It's the frequency of all the points we've accumulated up to this point. It's like a small fish getting eaten by a bigger fish, which gets eaten by an even bigger fish, and on and on. Each fish is now full of the fish it ate, and the fish that fish ate. And side note, your odds of being killed by a shark, a noted fish eater, are about 1 in 3.7 million. Back to our cumulative frequency plots. These plots have their moment to shine when we want to answer a question like, how many Justin Timberlake songs have 160 unique words or fewer? The cumulative frequency plot looks like this. And here's the bar that answers our question. We could also get this information by counting all the songs in the bars that are 160 or less on our histogram, but that's more work. Now that we've seen some good graphs and some bad, we can apply our newfound knowledge anytime we see data visualizations, which will be all the time. This I promise you. I mean, like, until the end of time. On the bus, in your health app, or during your boss's annual company-wide meeting, you'll know that graphs are only as good as the information they communicate. If you see a bad graph out there, say something, ask questions, be skeptical. I'm coining a new DFTBA today. DFTBAQ. Don't forget to be asking questions. It's another way of being awesome. I want it that way. The world wants it that way. And remember, it's not just gonna be you, it's gonna be me too. All right, I'm gone. See you next time. And yeah, I know I Want It That Way with Backstreet Boys.
Okay, that was a video. And we are 2 hours and 17 minutes into this live stream. And you, potential viewer, are either just joining us, or you have been joining us, or you've spent years joining us. Thank you. Thank you. I am swiftly falling asleep, but I appreciate everything that we've done today. We've laughed, we've cried, we've taken notes, and through it all, you've been there, supporting me, boosting my ego, telling me there's nobody else alive more worthy of your time than me, and for that I thank you deeply. With that being said, I'm probably gonna go now. But if you've enjoyed this content, once again, blah blah blah, give me money. You know the drill. Thank you so much. I am swiftly crashing. I'm gonna go do something else. I'm not sure what that is, but it will be something that I can guarantee. Until next time, have a great day, a great evening, a great summer. And don't forget to tune in next time. Thank you.